All right. YouTube tells me we should be live by now. So you're still seeing the intro screen, which is fine. Sound check. If anyone in chat can hear me, would be nice to just throw in a message saying we can hear you. But let me just put myself up as well so that people can see me. There's a little bit of a delay. At least that's what I noticed. And there might also be a commercial playing. At least I'm getting a commercial, so I'm just gonna skip that on my phone. I'm just using my phone to watch it. So I hope people can hear me. Otherwise, this is gonna be a very interesting stream with me talking and no one being able to hear me, but should be fine. All right, so for today, principal component analysis. It's one of the most used techniques in molecular biology, not just in molecular biology, but also in bioinformatics and, well, I think any field where people look at data and do data analysis, they have a principal component analysis. So without further ado, all right, cool. Chat says that they can hear me. Perfect. All right, so then we'll just jump into it. So this is what we want to talk about today, or this is what I want to talk about today, because I think that you need to understand all of these different subsections before you can start understanding principal component analysis. So we'll be starting off with autoscaling. It's one of these things that you have to do with your data. And then we'll be talking about the covariance matrix, eigenvectors and eigenvalues, variance explained. A little bit of a frog in my throat. And then we'll talk about PCA projections, because PCA is nothing more than a reprojection of your original data. And then we'll compare back to prcomp. Hello, Arnoop. Thank you for joining the chat. For some reason, I can't see the chat messages on my phone, so I have to look at the screen there. But it'll work out. And then something about interpretation. So basically, principal component analysis will start off by talking a little bit about PCA, what it means, how you can use it, how many principal components you should take, and then we just go through. So if anyone has questions during the live stream, just throw your questions in chat and I will get to them if I see them, because like I said, can't see it on my phone, but can see it over there. All right, so first off, what is principal component analysis? So principal component analysis is a dimensionality reduction method. So instead of having to look at 50 different features on 500 different samples, for example, what we can do using PCA is reduce the dimensionality, so look at the two main components against each other, right? So this will allow us to find like large scale clustering in data, or at least that's generally what we look at. So it is also used to compress and reduce the dimensionality of large data. So this compression is part of the PCA method. So it works very basically. So compression and reduction of data, right? So you can use, for example, a couple of principal component analysis to represent kind of the major vectors in your data. See, and now I can't read the chat properly because it's so freaking small. Autoscaling works like normally, or we have to separate work on the data. So that, if you do it from scratch, you need to autoscale your data first, because otherwise the covariance matrix goes haywire. But like I said, it's a way to reduce dimensionality, so it allows you to, in a single plot, look at the things which have like the major effect on your data. Not only that, but if you take the first principal component and you correlate it back to the features that you have, you can also find which features are contributing to one or two, or to the first or to the second principal component. So it's a very old methodology. It was invented in 1901 by Carl Pearson, the guy that also brought us correlation, covariance, and most of our linear modeling toolkit. So it's a very old method, 123 years now, but it's still used every day. Although there's newer methods nowadays like TS&E, which are different types of method. But the nice thing I like about PCA is that PCA draws from your data. So it's based on your data, and it doesn't use any of the labels that you assign to the different samples. So basically I have a little example here. So here we kind of see a normal axis, right? So we have like a variable which is plotted on the x-axis. We have another variable plotted on the y-axis. And then we want to know which are the main components of the data. So the main components of the data is, of course, the first component. You can draw a line, the red line here. So this red line here, this line here, this gives you the most variance, captures the most variance in your data, right? Because the variance in the x-axis, so in this direction, is larger than the variance we see like this. So the second principal component is always going to be orthogonal. So it's always going to be directly on top of the first principal component. So principal component analysis with two variables is nothing more than rotating the axis that you have, right? So if we would take the x-axis and we would start rotating the x-axis, then the y-axis would rotate as well. So at some point, once the x-axis is through most of the data points, right? So that the sum of squares of the data points to the x-axis is minimized, then those are the principal components. So when we do principal component analysis with just two features, it's relatively easy because it's nothing more than just rotating the axis to fit the data best. So principal components themselves, they are linear combinations of the original data, right? So we have the original data, and then when we do PCA analysis, the first principal component is just a linear component of the original data. That means that if we take all of the principal components that we have, which is generally the same number as the number of features, then the data that we describe is exactly identical to the original data that we have. So there is no loss in that sense, right? So there's no information being lost by doing PCA, but we can look at subsets of the data. So if we look at the first 5 principal components in a system where we have 20 features, then of course we are only capturing a certain amount of variance. But if we then would look at all 20 components themselves, then we would capture the whole original data set. So PCs are orthogonal. So orthogonal means that they are having a 90-degree relative to each other, like the x-axis and the y-axis in a normal plot. And this is important because this will come back, and this also helps us to interpret our data. Right? Because generally, when we have our data and our data consists of 60, 70 different features, then all of these features are collinear to each other in some way. It's very, very uncommon to have features, for example, the size of an animal and the length of the tail of an animal to be not correlated to each other. So the thing that principal component analysis does is it gives us vectors representing the original data, but each of these vectors are uncorrelated to each other. So the correlation between any two principal components is always going to be 0. So the variance explained by principal components decreases. The first principal component explains the most variance, the second a little bit less, the third even less, and so on until you hit the last principal component. And at that point, if you would sum up the variance explained across all of your components, you would have 100% of the variance explained, right? Because the original data is represented by a linear combination of all principal components. So what we can do is of course, the number of principal components that we can compute is always equal to the number of features that we have, but the number of principal components can also be smaller, right? If we have two features who are exactly collinear with each other, so there's no difference between them. For example, if we would calculate the body weight in kilograms and we would calculate or measure the body weight in grams, then these two things would be the same, right? So at that point, we will end up with one less principal component compared to the original data. So people always ask me, how many principal components should I keep? And the question or the answer to that is that it depends on your application, right? So depending on what you want to do, you might want to describe your data. So you want to get the main 2 directions in your data. Then if you want to only get like the main 2 components in your data, then of course you only have to use 2 principal components, but you can use a lot more. Hey Dion, welcome to the stream. So the number of principal components that you have and the number of principal components that you are going to use later on varies or depends a lot on what you want to do. So generally, if you think about QTL mapping or genome-wide association, you would take 1, 2, or 3 principal components to describe kind of the overall population structure, and you would regress those out of your phenotype generally. But it really depends on your application. There's nothing really to say how many you should use, right? If you want to just get your data to be completely orthogonal, then of course you want to keep all of them, because otherwise you start losing information. So the more principal components you include, the better you capture the original data, but the harder it again becomes to interpret them. So it really depends. All right, so for today we're going to do from scratch. So we're going to write our own principal component analysis, and we're not going to use any libraries. We're not going to use any packages. So we're just going to use R, basic R. All right, question in chat. I did not understand what you meant by collinearity of the data. If those two features have different levels of measurement, a PCA can be applied of them, height and weight. Yeah, so height and weight, they are collinear, right? Because generally the bigger a person is, the more he will weigh. But this is not a perfect collinearity, right? So there is still, if you would take both of the measurements, then still some people who are a little bit smaller than other ones will still be bigger than people that are, or they will still weigh a little bit more, right? So collinearity is when there is a more than a non-zero correlation between two things. Right? But of course, if we measure body weight in kilograms and we measure body weight in grams, then these two things are identical, right? So their correlation is going to be exactly 1. So at that point, a single principal component can more or less describe both of these features. So in that sense, we will end up with the number of features that we have without 1. All right, so from scratch, I think that, yeah, okay, perfect. So from scratch, so we're going to use a data set. So this is the data set that everyone uses in R. I like the data set. It's Edgar Anderson's IRIS data set. And it's a very, very well commonly used data set in R. It has 150 measurements. So it measured 50 different flowers from 3 species of irises. So you have the setosa, the versicolor, and the virginica. And just to make things clear, I plotted them here. So the setosa has this blue one. The versicolor, like the name says, can be many, many different colors, but I took a nice purple one, which has these like yellow and white accents on them. And then you have the virginica, and the virginica is a white one with a little bit of a bluish hue on top of it. So very beautiful flowers, very interesting flowers, and this is the standard data set that almost everyone uses when they do something in R. So it's just available. You can type data iris, and you'll have the data available in R. So it has 4 features. So they have measured from each of these 150 flowers that they had. They measured the petal length and width and the sepal length and width, right? So basically, if you have a flower, then the petals are the leaves that surround the flower, which are the nice colorful ones. And the sepal is where the stem transforms into the flower, and these are generally green leaves underneath the flower to support the more or less the flower shape. So again, like petal and sepal, they are relatively collinear with each other. And of course, the length and the width of the petal and the sepal are also collinear with each other a little bit, right? But in the end, it's just 150 flowers of 3 different species, and they measured 4 features. So that's the data set very basically. And of course, when we load the data in R, we can type data iris, and we have to get our values from it. So I want to transform these as a matrix. So I take the first 4 columns, which is petal length, petal width, sepal length, and sepal width, transform it into a numeric matrix and store this as values. And then there's the 5th column of the matrix, which contains the name of the species. So I'm just going to say as factor because it's a factorial, so a categorical variable with 3 levels. be it setosa, versicolor, and virginica. All right. So once we have loaded our data, we need to autoscale our data. So autoscaling in PCA is done to remove the effect of scale, right? You can imagine that if petals are between 50 centimeters and 1 meter, there's a lot of variance in the size of the petals, right? But if another variable has a very small range, so for example from 3 centimeters to 4.5 centimeters, then of course the first one is going to show a lot more variance than the second one. So to remove that, we need to more or less standardize our data, and in PCA, standardization is always done using autoscaling. This is also called unit variance scaling. Right, so basically it works like this. You center each column around 0. So you take a column of the matrix and you subtract the mean of the column. And then you normalize your variance. So normalizing your variance is done by dividing by the standard deviation. Right, so if you now have a phenotype which has a large amount of variance, it will have a large standard deviation. So dividing by it will mean that you end up with values which are generally, almost all values are between -1 and +1, right? So, and of course, since you centered your data, all the data becomes equally in size of units, more or less. All right, so this is the function that you can use to do autoscaling. So the autoscale function is relatively simple. So it's a function. It has a capital X as input, so capital X's. So generally in R, when you use small letters like this, small letter X, it means that you are looking at a vector, and capital letters you are denoted matrices. Right, so it gets a matrix as input. This matrix is called X. What are we going to do to it? Well, we're going to apply to X, to the columns, a new function. So this is an anonymous function. We're not going to name the function. But what this function will do, it will take the column that we're currently looking at, subtract the mean of the column, and then divide by the standard deviation of the column. And then we're going to return this whole thing back to the caller. Right? So that's how this function works. So we apply to the matrix, to the columns, this function to standardize every column by subtracting the mean and dividing by the standard deviation. So the next step is going to be computing the covariance matrix. So covariance means, or the idea behind covariance is that if you have two features, right, if one feature is higher than the average and the corresponding feature or the corresponding value of the other feature is also above the average, then that means that these two things are more or less similar, right? Because they are above the mean. Same thing for stuff which is below the mean, right? So the idea is that if you look at a vector of values for one feature and you have another vector of values for the other feature, after you've autoscaled them, values above mean that you are larger than average. Values below mean that you're smaller than average. So covariance works in this way by just saying, well, okay, so we have the mean of the column. So the mean of the column in our case is always going to be 0 because we autoscaled it. So the mean of X is going to be 0. The mean of Y is going to be 0. So what are we going to do? Well, we're going to take the values of X, then subtract the mean of X, and then multiply this by Y minus the mean of Y, right? So we have two different vectors, for example, the sepal length and the sepal width. And now we want to see how they covary. So if one of them is high and the other one is high, then this positively contributes to the covariance. While if one is low, so below the average, it's a negative value, and the other one is also below the mean, it also is a negative value. So you're multiplying two negative values together, which again becomes a positive value. Right? So the only way that covariance cancels each other out if one of the measurements of a plant is above and the other measurement is below, because then you get a negative value, which then subtracts from the covariance. Right? So the covariance function is here. Implementing it in R, you can do it like this. So what we say, again, we have covariance. It takes a matrix as input. And the first thing that we do is we build a new matrix filled with NAs. And this is because we want to have a matrix to store our covariance values in. Right, so we have 4 features. So the features are in the columns. So that means that we have a matrix which is 4 by 4. So it's 4 number of columns of X, number of columns of X. So it's a 4 by 4 matrix. And I'm going to give the names on the rows, and I'm going to give the names on the column, and that is just going to be sepal length, petal length, sepal width. So those are the column names of X. I repeat them twice because they are both the row names as well as the column names. Right, so in the first line, I'm making just an output matrix, a 4 by 4 output matrix, which has the proper names on the rows, proper names on the column. All right, and then I'm going to go through the column names of X. I'm going to go through the column names of Y. And of course, then I need to compute this term. So I'm going to call this Vx, right? So it is from matrix X, take column number X, and subtract the mean of this column. I'm going to do the same thing for Vy. So I'm going to take the Y column, the yth column from matrix X, and subtract the mean of the yth column. And then I'm going to just multiply Vx and Vy together, and then sum all of the values up. And then I'm going to divide by the number of rows of X minus 1. So the dividing here is standardizing based on the number of values that you have. It is minus 1 because you lose 1 degree of freedom. So that's kind of, you could argue about why not divide by n. It doesn't matter too much, but the covariance definition is to divide by n minus 1 because of the fact that you lose 1 degree of freedom because of the mean calculations. So we're going to do this for all of the columns. So I'm going to compare column 1 to column 1, column 1 to column 2, column 1 to 3, and so on. So I'm going to just iterate through all 4 possible, or through all 16 possible combinations. I'm going to compute the covariance, and then I'm just going to return the covariance matrix once I'm done. Right, so it's a very basic function to compute covariance. There's a function in R that does it as well, but since we're building it from scratch, I thought why not just show you the formula, explain you how the formula works, right? So if you have above average and above average, it adds to the covariance. If one of them is above average, the other one is below average, it takes away from the covariance value. And then in the end, we divide by the number of comparisons that we did, minus 1. All right, so this is going to be the hardest part because we need a third function. So the third function is going to be the matrix decomposition function because PCs are orthogonals, right? So we first have our data, we autoscale our data, and then we need to compute the orthogonal basis, so the eigenvalues and the eigenvectors of our principal component analysis, right? So we need to transform our covariance matrix into an orthogonal matrix because our covariance matrix still is not uncorrelated, right? So we can do that by decomposition of a matrix into a product of matrices, right? So we have matrix A, which is our covariance matrix, and now we want to define A into 2 separate matrices. So we want to split it into matrix Q, which is orthogonal, and then we have matrix R, which is the upper triangular matrix. So by multiplying Q and R together, I get back my covariance matrix. But I can use then this matrix Q to then have to then multiply my data to, right? Because matrix Q is orthogonal, so that means that if I would take my autoscale data, multiply it by the Q matrix, then now I end up with a score matrix, and the score matrix is the principal component matrix because the first principal component is on the first column, the second principal component is on the second column, right? Because Q is a big matrix, it will have the eigenvectors. That is how we compute it. So we can take the autoscale data and then we can project it using the Q matrix, and now we have our principal components, right? So the eigenvectors of the Q matrix, you can think about them as the axis rotations, right? So if we have two orthogonal axes and we have two features, then the Q matrix is nothing more than a rotation of the two axes, so a rotation of the first axis to more or less change the perspective at which we are looking at the data. So that is how principal component analysis works. It is nothing more than modifying and tweaking the axes at which we are looking at our data. So orthogonal means that everything is independent of each other. So like I said, we need to decompose our matrix into a product of matrices. So we take our covariance matrix, we then compute an orthogonal matrix, which multiplied together by this upper triangular matrix causes these two matrices combined to be identical to A. We then take our Q matrix, which now has the eigenvalues, so the different rotational vectors for the different axes. If we then multiply that with our autoscale data, we end up with a score matrix of which each individual column of the score matrix is going to be the principal component. So this looks like a lot of magic, and it kind of is, because linear algebra or matrix multiplications generally are relatively magic. But this is something that you just have to, well, I would say deal with. No, it's not deal with, because you can learn how it works, but it takes a lot of time to read up on how to do decomposition, right? Because in the end, it is something which is very similar to kind of projection matrices in computer graphics, right? So if you do computer graphics, you also have like a triangle, which you then multiply the vector or the quaternion of the triangle. So each individual point, you multiply that by a projection matrix to put it somewhere in the 3D world that you are creating. So PCA is the same, but it just doesn't do it in three in three dimensions. It does it in X dimensions, where X is the number of features that you are looking at. So we compute the eigenvectors here through the Gram-Schmidt process, because eigenvectors cannot be, well, for a 2x2 and a 3x3, there's always going to be a single unique answer. However, for larger problems, you can only numerically approximate the eigenvectors. So that is the way that it works. So we need to compute Q, the eigenvectors, through something which is called the Gram-Schmidt process. So you take an initial estimate and then you refine the estimate the further you go along. So how do we compute that? So, well, we compute the eigenvectors through QR decomposition using the Gram-Schmidt process. So what we do is we take a function called eigenvectors, we define it as a function which as an input takes a matrix X. So in this case, X is not our data matrix, it is our covariance matrix. So it takes the 4x4 covariance matrix, and then we set a number of iterations, right? So the more iterations we do, the better our estimation of the proper eigenvector matrix. But if we do too many iterations, this process will slow down quite tremendously. So there is actually a way to make it stop, because at some point it won't improve further, right? So at some point we have the best basis, the most accurate representation of the not of the principal component, but of the eigenvectors. And from that point on, the matrix won't improve anymore. So in theory, you could have an if statement here, which quits after the matrix doesn't improve anymore. So what are we going to do? We're going to set P of Q as the identity matrix. So we take a diagonal matrix, which means that it's just a matrix which is composed all zeros, but the diagonal is just ones, right? So this is going to be our Q matrix eventually, right? So we start off with a Q matrix, which is a diagonal matrix, and then we are going to compute both the Q matrix and the R matrix based on our input value X. So how are we going to do that? Well, we're going to go and we are going to iterate, in this case 100 times. So we're going to make 100 updates every time we're going to compute the QR decomposition. So we're going to decompose matrix X into a Q matrix and an R matrix, right? So a Q matrix and an R matrix. So we take X, we compute the QR decomposition. We're going to take the Q matrix and call it Q, and we're going to multiply this Q matrix created from X to our identity matrix PQ, right? So PQ is the matrix that will be updated time and time again. So we are going to matrix multiply PQ times Q. So we have Q. And then what are we going to do? Well, we're now going to reconstruct what is left of X. So what are we going to do? We're going to take the R matrix of the original QR decomposition, and we're going to multiply that by the Q that we also decomposed, right? So it's basically nothing more than multiplying the two decompositions together to reconstruct our X matrix. And then we're going to do this again. So the only thing that is really changing is the X and the P and the Q. So the PQ is going to contain our eigenvectors, while the X matrix, after we're done, is going to contain our diagonal. So this is going to be the R matrix eventually, right? So once we are done, we take the diagonal of X, which are our eigenvalues, and then the eigenvectors are the columns of P and Q, which we can now use to multiply with our standardized data. All right, so 3 functions. I hope it's clear how we kind of build these functions, why we need this function. So the autoscaling is there to make sure that all of the data is normalized so that we can compute our covariance matrix. Our covariance matrix tells us how features are related to each other. If one of the features is high and the other one is high as well, it contributes. If they are low, then it also contributes. But if they are unequal, then it doesn't contribute. So it gives us a measurement of how related the different features are, right? So a high number for covariance means that two things are very similar when it comes to looking at them, while then the QR decomposition will give us more or less the basis for computing our principal components. All right, so let's put it all together. So I'm gonna switch to R and just chuck in the different matrices. So let me open up Notepad++. So here we have the 3 functions. We have the autoscale function, we have the covariance function, and we have the eigenvector decomposition function to compute the eigenvectors and the eigenvalues. All right, so I'm gonna copy this and I'm gonna go and show you guys R. So I'm just gonna copy paste this in. Right, so very basically we have now an autoscale function, right? So if we have a vector, so let's just do a vector 5, 6, 8, 52, 32, 92, 6. Those are not commas, right? So I'm just gonna make a little vector, right? So what this is going to do, I'm gonna call this X and I'm going to say autoscale as matrix X, and then I need to transpose it because I think if I do as matrix, no, other way around. So it does create a matrix the way that I want. Right, so here you see how autoscaling works. So it tells you that, well, okay, so this is the value, these are the numbers that we inputted, so it's going to be the column of our matrix. So what I'm doing is, or what it does, it computes the mean, and then it computes the standard deviation, and then it's subtracted. So it means that the original number 5 is negative 0.7 standard deviations away from the mean value, while this large value, 95, is 1.93 standard deviations above the average of the vector. Right, so that is how autoscaling works. So covariance, so let's load the data set of iris so that we can actually do that. So I'm going to load data iris and I'm going to make sure that we have our values. So let's look at the first 10, right? So 1 to 10, so first 10 rows. So this is how the values look like. So here you can see the 4 vectors are the 4 columns that we have. So the 4 features that were measured on these iris plants. So we have sepal length, sepal width, petal length, and petal width. And then we can just standardize them, right? So it could take the sepal length column and then say autoscale, right? So again, it would transform. Sorry. We need to do at least 2 columns in this case. Right, so I'm taking the first 2 columns. So the first 2 columns are 5.1, 3.5. So if I'm autoscaling it, it tells me that 5.1 for sepal length is actually below 0.9 standard deviations below the mean, while a sepal width of 3.5 is actually 1 standard deviation above the mean. Right, so a value of 0 means that it's exactly similar to the mean, and any positive value means that it's that many standard deviations above the mean, and negative values that many standard deviations underneath the mean. I have my values, right? So let's look at values 1 to 10 again. So that's how it looks. And then I also have my labels. I think I called it labels. So let's look at the first 10 labels. So the first 10 are all setosa plants. So these 10 measurements all come from setosas. All right, so we have our data loaded. So then the next step is going to be to look at do the computations, right? So I'm going to take my values, I'm going to autoscale them, and I'm going to call this STD, so for standardized values. Then I'm going to compute the covariance matrix, and then I'm going to compute the eigenvectors and the eigenvalues using our eigenvector. So like I said, we're doing it from scratch, so it's good to see all of the functions and how they exactly tie into each other. But all of these functions have built-in functions in R. So covariance, you can use the cov function, which is the built-in covariance function. And eigenvectors, they have the eigen function. So you can use eigen as well, but we're going to use eigenvectors for our own. All right, so let's check back into R. So I'm going to just do the computation, right? So I'm going to load our data, I'm going to subset it, and then I'm going to compute the STD. So these are the standardized values, which we already saw, right? So first 10, again, minus 0.9 standard deviation, 1 standard deviation above the mean, under the mean, under the mean, right? So if I look at my covariance matrix, so if I look at my covariance matrix, the covariance of 2 things will always be 1, right? Because sepal length and sepal length, they are 100% the same thing, so their covariance is going to be 1. Of course, it doesn't matter which direction I take, so the upper triangle of the matrix is going to be equal to the lower triangle, right? Because it doesn't matter if I compute the sepal length versus sepal width covariance, it's going to be the same when I do the reverse, so when I do the sepal width computation against the sepal length computation. Right, so here we see that sepal width and sepal length are actually negatively covarying with each other. So that means that the larger the sepal, the smaller the width of, so the larger the length of the sepal, the smaller the width of the sepal. So that kind of, if you have a flower, you can think about, well, you can make a very long petal or sepal, and then you will have very, very small the width of them. While the sepal length and the petal length, they are really correlated with each other. Or I'm saying correlated, but they co-vary with each other quite a lot. Right, so 0.87, that's pretty high. So that means that the longer the sepal of a flower, the longer the petal of a flower. And the funny thing is that you can see that the sepal length is also positively covarying with the petal width. So it just means that the longer your sepal is, the larger the petal that it can support on the flower. Petal length and petal width are even higher correlated to each other, so they are very, very similar. So, but you can see that for sepals, it doesn't hold. So sepals are not, the length of the sepal is not related to the width of the sepal, but when you look at petals, then the petal width and the petal length are highly correlated to each other. All right, so then when we look at our eigenvectors, I call those EVFs. So if I look at my eigenvectors, then it computes here the eigenvalues. So those are the diagonal of the R matrix after decomposition. And this is my eigenvector matrix. So the first eigenvector is here. So it assigns a value of 0.52 to the sepal length. It assigns a value of minus 0.26 to the sepal width, 5.8 for sepal petal length versus sepal length, right? So the columns here are unitless, but they do kind of relate to how you should rotate it, right? So the nice thing about eigenvectors, which I told you, so if I would take the vectors out and I would just compute the correlation of them, then the correlation of them should be 0, which it is not, which is strange. No, let me see. I need to transpose those. So you can see that they're not exactly 0, which is, oh no, sorry. It's not the eigenvectors that are uncorrelated, it is the principal components that are uncorrelated. So I'm messing up myself here. I'm confusing eigenvectors for principal components. Anyway, let's go back to the presentation. Right, so we can autoscale ourselves, compute the covariance, and then compute the eigenvectors. And we can use the eigenvectors to make the data uncorrelated into principal components. All right, so if we want to know how much variance can be explained by each of the principal components that we're going to calculate, we can actually use the eigenvalues. So the variance explained by the individual principal components can be computed by the nth eigenvalue divided by the sum of all of the eigenvalues. So we can compute the variance explained like this. So we can say I take my eigenvalues and I divide those by the sum of the eigenvalues, right? So then I get a vector where each of the values is divided by the sum. I multiply it with 100 and I round down to 1 digit behind the comma. If I then want to see the cumulative sum, so the cumulative sum should always be 1 after the number of components, right? So in this case, we have 4 features, we have 4 components, 4 vectors. So if I sum them up, they should be 100. And then I can visualize it. It leads to a plot which looks like this, but let's very quickly do that in R, right? So if I compute the variance explained, so I'm going to just say variance explained, right? So I round, so I take the eigenvalues, so that's 2.9 divided by the sum of this. So that's not, it's 2.9, 3.8, 4.2, 4.2. So it's like 2.9 divided by 4.2. You see that the first principal component is going to explain 73% of the data. The second principal component is going to explain 22.9%. The next one 3.7%, and the last one 0.5% of variance explained. So using the cumsum function, we can do the cumulative sum. So if we do CVE, cumulative sum, we see that just it doesn't add up to 100, it adds up to 101, but that is because we rounded them, right? If we would not round the variances explained, so if we would just say don't round them at all, just multiply them by 100, right? So variance explained, do the cumulative sum, then now you see that it will add up exactly to 100. So by rounding it, we kind of introduce a little bit of a skew, but that's how it works. All right, so we can basically just plot the cumulative variance explained, and then we get our graph, which looks like this. So we can see that the first component explains around 73%. The next one, so the first 2 components combined, explain 95.8% of the variance seen in the data. And then the third component combined, we are already up to 99.5% of the variance explained. Right, so the variance explained in this case tells us how many components we should or can take to represent our data. So in this case, you would say, well, with 2 principal components, I'm catching 95% of the variance that is in my data set. So the 2 principal components should be enough to accurately represent the data that has been measured. All right, so variance explained. So the next thing what we want to do when we want to compute our own principal components is to do the PCA projection. So it reconstructs the iris data as a linear combination of the original data, right? So that is what PCA does. So how can we do that? Well, we can take our standard data and then multiply it by the projection matrix. So we can compute the projection matrix, which is the principal component matrix. So we can take all of the eigenvectors, we call that W, and then what we do is we multiply our standardized data together with W, right? So if we do that, we can put the column names on. So now P will be principal component 1 in the first column, principal component 2 in the second column. All right, so let's do that in R so that you guys can see it as well. So P, right, so this is now the principal component matrix for our data. So if we now would calculate the correlation of P, then now all of them should be more or less 0, which you can see that is the case. It is 1.4 times 10 to the minus 16, right? So of course, every principal component is 100% correlated to itself, but it is uncorrelated to all of the other principal components, right? So that now means that each of these vectors of data is independent of each other, is catching one unique axis of data. Right, so if you would think about it in a 2D plane, what we did is if we have the sepal width and the sepal length, just 2 vectors, right? What we just did is we just rotated the axis so that the first axis catches the most variance and the second axis catches the other remaining variance in the data. All right, so we have our projection matrix, so we have computed our own principal components, so that is more or less what we set out to do. So next step is also we can do a partial reconstruction, right? So if we are thinking about compression, then what we could do, instead of storing the original matrix, we can actually store part of the principal component matrix. So if we want to get a scaled down kind of image or a scaled down matrix of the iris data set, this would mean that we would be able to store just the first 2 principal components. Because with just the first 2 principal components, we can reconstruct 95% of the variance in the data. So that means that we could compress this data set by around half. So that means that instead of storing the 4 features, we could store the first 2 principal components, and the first 2 principal components would still be good enough to reconstruct most of the variance. Right, so if we would do that, let me show you guys how we can do that. So I'm just going to go to Notepad, right? So I'm going to take the first 2 columns of the W matrix, I'm going to multiply them together, and then I'm going to do P, right? So now we see that P is a 2-column matrix, and it's still an uncorrelated matrix. So if we calculate the correlation of P, we can still see that these are 2 things which are independent of each other. And if we would plot matrix P, then it shows us that this is kind of the structure in the data, right? So it will tell us the loading on PC1 and the loading on PC2. But let's go back and let's take all of the eigenvectors to do P, and then we would plot P, and then we see that there's almost no difference. But that is because the first 2 principal components already caught 95% of the data. So I realize, that you didn't see R. All right, so let's do it again, right? So let's go up. So what we want to do is we can do, so this is when I look at the first 2 principal components of P after I've used all of the eigenvectors, right? So it looks like this. So if I only take the first 2 eigenvectors, then you can see it looks almost identical. Almost none of the plots or almost none of the points have moved. But that's because the first two principal components contain more or less the same amount of information, or 95% of the information, relative to the whole principal component matrix. Right? So instead of storing a matrix which has 150 entries, 4 columns, I could just store 2 columns, 150 entries. So virtually reducing the data set by around 50%. Anyway, I'm just going to switch back to Notepad, right? And I'm going to make sure that I use all of the principal components, all of the eigenvectors to compute the principal components. So let's do that and then do a little plot to make sure that it's there. So plot, and you can see that they barely move the points. So barely move. Again, I realize you guys are not looking at R. So they barely move, right? Almost identical. All right, so let's start visualizing it, right? Because this is one of the visualizations that we can use. Principal component 1 versus principal component 2. That's generally the two that catch the most variance. So what if we compare our from scratch PCA to the built-in prcomp function, right? It should be very, very similar, should be identical. So the way that I'm going to do this is by saying I'm going to make a plot which has 2 windows. So there's 2 plots inside a single window. So I can do that by setting the parameter mfrow to say I want to have 1 row, 2 columns, right? So it's a 1 times 2 plot. So 1 row, 2 columns. So I do the first plot. So I'm plotting the principal components from scratch in the first, so on the left side, and then on the right side I'm going to plot the built-in prcomp function, right? So our principal component matrix is called P. So from P I'm going to take PC1 and PC2. I'm going to color by the labels. I'm going to give it a main so we know which one is which. And I'm going to do PCH is 19 to have filled circles. And then I'm going to put a legend there, which is going to be on the bottom right. The levels are going to be the labels, so that I'm going to take the levels of the labels. So that's going to be Setosa, Versicolor, and Virginica. And the colors are going to be the unique labels, because here I use the labels, the factor as the colors, same PCH. So in R, doing principal component analysis is just a single call, right? So you can do prcomp on your values, scale is equal to true, right? So here, there is no auto-scaling that you need to do. No, you can just give the prcomp function the values, and then you can say, well, I want to auto-scale them. And then from this, extract matrix X. So matrix small x in the return of the prcomp function. That is the principal component matrix. So this is called PCA. So I can then plot the PCA. Again, I'm going to take the first 2 columns. I'm going to take the labels, make sure that I know which one is which. All right, so let's check to R. Sure that we can see the R window. So let's do the little plot so that we can compare both of them together. So I'm going to make sure that my window is a little bit broader like this so we can fit all 2. Right, so and this is what we see. We see our from scratch principal component analysis and then the function prcomp. All right, so first question. Could you elaborate more on the value of PC1 and PC2 and they explain the data repartition? Yeah, so PC1 and PC2 are, so the data in the PCA matrix is exactly the same as the data in the original matrix, right? If I use all principal components. It is just that it's a different projection, right? So instead of having one axis, which is petal length, another axis, which is petal width, and then a third axis, which is sepal length, and another fourth axis, which is sepal width, I now have 4 axes which are not related to the original measurements, but they are capturing the exact same pattern, right? If we could make a 4-dimensional cube, then in the 4-dimensional cube, the data has not changed. The only thing which has changed is the axis system that we are using to project the data. So instead of having a data axis, which we can understand as being sepal length, we now have a first x-axis, and the property of this axis is it explains the most variance in the data. The second axis is the y-axis, used to be sepal width, but now it is the axis which explains the most variance except for the other axis, right? So it explains the second most amount of variance. So the data doesn't change, right? The data is still exactly the same as it was. It is just that we move the axis system. So having 4 axes which we have measured, petal length and width, sepal length and sepal width, we now have 4 different axes through our data, but the data is still exactly the same. Also, what does this plot exactly mean? PC1 versus PC2. How do we analyze PC in the context of the iris data? Yeah, so here in the context of the iris data, we might want to know, are these 2 different plants? Or are these 3 different species? Right? So if we look at the first principal component, we see that the data kind of splits out into one very clearly distinct group. Right? So we can see that the setosa is on the first principal component axis. I can, very basically, I could just say, well, if the loading of the plant or of the measurements is below -1, it is going to be a setosa, right? But for the other 2 species, it's not that clear. We can see that the versicolor and the virginica, they overlap each other in the middle here, right? So that means that these 2 species on the first principal component axis, they are not separated, right? So it means that there's no clear phenotypic difference between these 2 plants when we just measure these 4 variables. So from these 4 variables, we can uniquely identify the setosa, right? So the setosa is clearly different from all of the other plants, but the versicolor and the virginica, they are not uniquely separable on the first principal component. The second principal component in this case doesn't add anything. It doesn't allow us to distinguish better, right? We could say, well, if you are high on the second principal component axis, right, above 1, then you are either a virginica or you are a setosa. But the main difference between these plants, like 75% of the difference in these measurements, is just captured in the first principal component, and it allows us to distinguish setosas from the other 2 species very clearly. We can see that the virginica on the first axis is slightly higher values than the versicolor, but they are not separating. So they are not separating out of each other. So it still means that if you would want to make a determination saying, are these really 3 different species or are they just 2 different species? The answer here would be is that, well, there's some evidence to say that they are 2 species and that the versicolor and the virginica are more or less similar to each other still, based on just having these 4 measurements on the sepals and the petals, right? Because we only have 4 measurements to start off with. We don't have the color or other things that we look at, right? So the idea is that the loading on the first principal component tells us if we can separate out the groups based on the most, or the axis with the most variance. So if we want to know, right, so if we look at so very basically, if we have our matrix P, right, and we look at PC1, right, so let's look at PC1, right, so these are our values. So if I correlate this to the original values that we had, right, you can see that petal length and petal width is highly loaded on the first principal component, as well as sepal length, right? So you can see that the correlation is almost 0.99. So that means that the first principal component axis is a combination, or is mostly looking at the petal length, right? So it's looking at the petal length and it's including a little bit, or 0.9, the sepal length, right? So it's a combination axis. So instead of having one axis, which is sepal length, this axis is catching variance mostly from petal length, a lot from petal width, but these two things are relatively correlated to each other, and also a little bit of the sepal length. If we look at the second principal component, right, so we can just say the correlation of PC2 to all of our values, then we see that the second principal component actually catches the variance which is in the sepal width. Right, so if we want to annotate our axis, then the principal component y-axis is the sepal petal length axis together with the petal width axis. The second principal component is the axis which catches the variation of the sepal width and a little bit of the sepal length. Right, so this is how we can take PCs and kind of deconstruct our data into unique vectors. But these vectors are uncorrelated to each other, and that is the advantage. Because they are uncorrelated to each other, it means that we can look at one axis and then look at another axis and put them perpendicular to each other, right? But because if we would do that for sepal length and sepal width, we would not clearly see this difference. All right, so let's go quickly back, right? So I also put the plot in the presentation. So I put here, right? Because if we look at our from scratch principal component analysis, it looks slightly different than when we did the prcomp, right? So we can see that there are slight differences. So what are those differences? Well, there are no differences because PCs are linear combinations, right? So a principal component is just inverted in our case. But that doesn't matter, because it doesn't matter if you have the x-axis on the, or if you have the y-axis going from -1 to 1, or if you have it go from -1 to 1 the other way around, right? So in the end, it's the same thing, right? -1, -1, and -1 is the same as 1, 1, 1. It's just in the opposite direction, right? So since they are linear combinations, they can be orthogonal. And of course, being orthogonal in the perpendicular direction is the same as being orthogonal in the other direction, right? So how do we fix this? Well, we just flip it around, right? So we just flip it around, and then you can see that they're exactly the same PCA plot, right? So that's the fix. Of course, we can do this in R as well, right? So in R, when we have our plot here, so the only thing which I have to do when I do my plot, so let me do my plot again. Let me get my code for the plot. Let's go back to Notepad. So the only thing that we can do is, if we want to do this, then I know now that on the x-axis I want to have PC1, right? Not just PC1 and PC2. And I can say on the y-axis I want to have PC2, but now take the negative value of PC2, right? So I'm just going to say negate the PC2 value, and on the x-axis put the PC1 value. So if I will do it like this, right? So now when we look at it, we can see that they are exactly identical. So the value here is exactly like that. Oh, crap, you guys can see that again. I'm not paying attention to which window I show. Right, so if I put it in and I say on the x plot PC1, on the y plot the negative of PC2, then now they look exactly identical. And of course now I need to move the legend up to here as well so that it doesn't overlap the points here. But you can see that they are exactly identical. All right, so let me go back to the presentation. So we can just fix it by flipping it around. No issue whatsoever. So we can flip the whole figure, or we can just flip the PC2 axis, right? So that happens often in principal components because it's the same thing. They are linear combinations, so it doesn't matter if you project it in the positive direction or if you project it in the negative direction, like it's doing here. All right, so that's actually everything that I wanted to say for today. So principal component analysis, it depends on you doing autoscaling of your data. You then compute a covariance matrix. You then compute the eigenvectors and the eigenvalues using the Gram-Schmidt process. You then compute your variance explained based on the eigenvectors, and then you can do a PCA projection, which means taking your standardized data matrix, multiplying it with the eigenvectors, and then you have a re-representation of your data in principal component space, so in orthogonal principal components. And then we compared it back to prcomp, and then we talked a little bit about the interpretation. So principal component analysis, it's used a lot to find groups in data, to see how well things separate from each other, but also to see how reproducibility is in experiments, right? Because the closer things cluster on the first two principal components, the less variance there is. And so if we would look at this, and we can see that these the setosas, they cluster really, really well on the first principal component. So there's no real variance in the setosas when it comes to the sepal length and the petal length. And we can see that because of the fact that these two are highly correlated to the principal component 1. So that means that when we look at setosas, they don't have that much differences in sepals or in petal lengths. If we look at the versicolors and the virginicas, right, so these have much, much more spread. So if we would look at the data and we would, for example, look at the petal length, right, then I would assume that if I make a histogram of the values, right, so I'm just going to take values, I'm going to say which labels is setosa, and then I'm going to look at the paste petal.length, right? So this is a histogram of the setosas, the petal length. If I would do the same thing for the versicolor, then you can see that these vary from like 1 centimeter to 1.8 centimeters, but these vary from 3 to 5.5 centimeters, right? So here there's only a 0.8 variance, and here there is a 2.5 variance, right? So that is caught in the principal component plot as well, because that's what we see here. So there's less variance in the petal length of setosas relative to the other two species, right? So we can use it to interpret our data, and we can kind of reason about what we see. Same thing would be if we look at the second principal component axis, which is the sepal width axis, right? Because it's highly correlated to the sepal width. We would assume that if we would look at the sepal width from setosa, that there's more spread in the setosa sepal width than there is in the versicolor, right? So let's check that, right? So if we do the same one again, but now we do the setosa petal width, petal width, probably with a capital, and we do the versicolor petal width, right? We would see that this one varies 0.6, this one varies 0.8. So not entirely, but that's also because the correlation is not, it's not 100%, but we can see that there's at least the same, kind of the same amount of variance in the petal width between the setosas and the versicolors, which is kind of what the second PC tells us a little bit as well. Because I would have expected it to be a little bit less, but there's a massive outlier here in the setosa. So the setosas range from like -3 to 1, so that's 4, and these ones go from -1 to 2 something. So I would have expected the sepal width to be a little bit less variable. All right, so are there any questions so far? I understand that it's difficult, like if we would if I would have to explain eigenvectors and eigenvalues all the way from 0, it would involve doing a whole linear algebra lecture, right? So all of these things, you can easily find very good starting points on things like Wikipedia, right? So if you want to learn more about eigenvectors and eigenvalues, definitely take a look at Wikipedia. They have very good citations to original literature that you can read. There's there's probably like other YouTubers who do like a whole linear algebra lecture from scratch, right? So because you want to start off with what is a vector, multiple vectors together, they form a matrix. You can transform vectors. So how do you do that? So in this case, because I just wanted to give you a high-level overview of PCA, so what is needed, autoscaling, covariance, eigenvectors, and eigenvalues. Normally, people just use the prcomp function in R, right? So they just use prcomp. They don't think about what is happening. A lot of people actually forget to set the scale is true, right? Because you do need to do autoscaling always. So the default is false in prcomp. And this is not due to scaling not being needed, but this is because of backward compatibility. So these are the steps to do your own PCA. Normally people just use the prcomp function and that's it. And then they plot the first two principal components, they look at it, and then they try to interpret what's going on. But you can do much more with it. So you can modify. So instead of covariance, you could look at the compute the eigenvectors and eigenvalues based on the correlation as well. So it allows you more flexibility to know how principal component analysis is working. All right. So if there's no further questions for today, then that's what I wanted to talk about. 1 hour, 11 minutes. Not too bad. Not too bad. I've gotten some complaints that my videos are too long, which I can understand. Like I tend to rabble on about things that don't really matter too much. But it's the way that it is. So I might go back to streaming on Twitch and then cutting it up so that you guys get like bite-sized videos. But I do like doing the streams, so I might just keep them on YouTube. All right, so no further questions, then I'm wishing you all a very happy Sunday. Thanks for this lesson. If total PC1 and PC2 accounts for less than 50%, should we present more components? Yes. Yeah, well, you always, like, principal components, they are related to the original data sources that you had, right? So if you have 60 different features, of course, the first two principal components are not going to catch all of your variation, right? Because if you start off with 60 features, you probably need like 5 or 6 or 7 to explain a reasonable amount of variance. But also, what is a reasonable amount of variance is very dependent on what you're doing, right? So one of the things that I always do when I do PCA is do the correlation of the PCs back to the raw unscaled data that I had to see what is causing, or what is how are these original phenotypes loaded onto the PC. But yeah, no, generally you want to have 2 or more components. You want to, or if you have 60 features, but you want to end up with like 80% to 85% variance explained, because those are kind of the main directions in your data, right? So if you need 4 or 5 components to hit this 80% explained, you would plot PCA 1 versus 2, 1 versus 3, 2 versus 3, 1 versus 4, 2 versus 4, 3 versus 4. And you would look at all of them to see if you see any clear grouping, right? Because this clear grouping will allow you to do predictions as well, right? Because if we now measure a new setosa, we then do the computation, right? So we multiply the values that we obtain with the projection matrix, and it ends up being, right? So it ends up being a negative scoring one. So we would know that the measurements come from a setosa, right? So we can take 4 measurements of the plant, measure the 4 things, multiply this with our eigenvector matrix, and then it will get 4 new values, which would then allow us to determine which plant it is without knowing it, right? So PCA can also be used to predict what you are seeing based on the phenotypic measurements that you have. All right, so thank you guys for spending your Sunday with me. Please like the video stream and subscribe to my YouTube channel if you want to see more. You would apply electrometabolomic data analysis like the one on RNA from scratch. I am working on that, Dion. I am working on that. I've been doing a lot of metabolomics recently, and I almost have a working pipeline, very similar to things like MetaboAnalyst, MS-Dial, which goes from raw machine output through all of the different steps that you normally need to do, like scaling scaling the profiles, and then determining features, and then doing feature annotation. So I am planning on doing one of those in the futures. There's also a QTL lecture that I'm currently preparing based on a request from not last week, but the week before that. So from the last stream, someone asked me, could you do a lecture about QTL? So there will definitely be a QTL lecture, and there will definitely be a metabolomics lecture. Once I get the preprint out for the QTL mapping work that we've been doing on the UMHET3, there will also be a video about how to do longevity analysis on the UMHET3 mice that we're currently been doing. So there's a lot of things in the pipeline. It's just finding the time to make them. But metabolomics is definitely on my list. Like I said, I've almost got a fully working pipeline, and then we will do metabolomics from scratch. And then it's going to be fun. All right. Thanks so much, guys. Enjoy the rest of your Sunday. I hope you have better weather than me. Like here, it's been gray and raining the whole weekend. Well, mostly the whole week. So yeah, it's been a poor summer here. So I hope that you guys have nice, beautiful weather, and that you can spend some time outside. All right, then see you guys next time. Ciao.